My name is Eugene Chang, and it's my privilege as chair of the Department of Astronomy to welcome you to this year's 2017 Raymond and Beverly Sackler Distinguished Public Lecture. Since 1993, the Sackler family has provided funding for an annual public lecture in astronomy as part of their effort to further the arts and sciences at Berkeley. The Sackler family is unable to attend today, but they will be given a video of today's lecture. And so on behalf of everyone here, thank you from across time and space. So the Sacklers have given to astronomy, and astronomy has always been about the big picture. And in this regard, I think there's really no other astronomer I can think of who has done more to widen our field of view and to take the biggest possible picture on the largest possible scales than our speaker tonight, Sandra Faber, Professor Emerita of UC Santa Cruz, Astronomer Emerita of UC Observatories, and one of the most influential extragalactic astronomers and cosmologists of our time. The difficulty in taking the big picture in astronomy is actually twofold. It's not just a matter of taking the picture. That is, it is not just a matter, the difficult work of designing the instrumentation and the equipment that enables you to actually snap the picture, but after you've taken it, there is the equally challenging part of deciding just how big the picture it is that you've taken. And this second problem is the classic astronomer's problem of calculating distances to objects. Sandy has made fundamental contributions to both problems and to many more. In the instrumentation side, she was pioneered the development of the Keck 10-meter telescopes and the Hubble Space Telescope and the associated cameras and spectrographs. And on the distance problem, she and her graduate student, Robert Jackson, discovered a relation between the luminosities of galaxies, and by luminosities I mean their total power light output, so the total wattages of these galactic scale light bulbs, a connection between the luminosities of galaxies and how fast their component stars are moving. So when you take a picture of a galaxy, right, and for the most part they look like sort of fuzzy spots, you don't know how far away the galaxy is, right? Because you can measure how bright it is, but for a given apparent brightness, you don't know whether that object is very close to you and just contains the light of a few thousand stars, or whether it's really, really far away and burns with the light of billions of stars. You can't distinguish between those possibilities. But Sandy could, and the way she did that was by establishing a connection between the luminosities, the total power outputs of galaxies, whether they contain thousands or millions or billions of stars, and she connected the luminosities to another property of the galaxy that she could measure that was independent of the distance, namely how fast the stars were moving relative to one another. These stars and galaxies, they're like bees in a swarm. So she could measure how fast the bees were buzzing around, whizzing about relative to one another by virtue of their Doppler shifts. So the faster the stars move, the more luminous the galaxy, and what has come to be known to generations of astronomers as the Faber-Jackson relation succeeded in calibrating the luminosities of galaxies, and by extension their distances, and literally put galaxies on the cosmic map. So this put us on the road to understanding their masses, their internal dynamics, and the formation histories of galaxies. Now, a lot of people, they would be more than happy just to sit back and enjoy the fruits of their labors, especially a landmark discovery like this. I've heard it said that if your work makes it into a textbook, then it's time to retire. And I defy you to find an astronomy textbook that does not feature the Faber-Jackson relation prominently. But not Sandy. She published this paper just 4 years after her PhD and has since gone on to make really fundamental contributions to our understanding of galaxies and the universe. She led the community to appreciate that most of the matter in the universe is dark, that not only is it dark, but it's cold. That is, it's lumbering along at speeds much less than the speed of light. She led a team of 7 astronomers that were dubbed the 7 Samurai to map out galaxies on the largest possible scales, so mapping superclusters of galaxies. And she established, through her leadership of the nuclear collaboration, so she has a real knack for names. They sound very intimidating. In her leadership of the nuclear collaboration, she established that in the cores of every galaxy, there lies a supermassive black hole. And not only that, but the properties of that hole, namely its mass, is intimately connected to the properties of the host galaxy. So her awards really are too numerous to list. I'll just mention a couple. In the Lifetime Achievement category, she was awarded a university professorship. This is the highest honor accorded a faculty member by the University of California. And she was also awarded a National Medal of Science, which was bestowed upon her by President Obama. Sandy's lecture today, as you can see, it's entitled Cosmic Knowledge and the Long-Term Strategy of the Human Race. In one sense, is perfectly in keeping with her career-long insistence on asking the biggest questions framed in the biggest possible pictures. But in another sense, is just really out there in a sort of X-Files kind of way. Sandy has been quoted as saying, this is a direct quote, "Astronomical knowledge is probably the most important single discipline that you need to know in order to be an informed citizen of Earth." And I have to confess, when I read that, I wasn't quite sure if I agreed. In our troubled age, I might have pointed to a few other subjects, energy policy, environmental studies, computing, biology. So I am very curious to learn what Sandy is going to teach us today. In this, as with so many other questions, we have looked to her, and we continue to look to her for intellectual leadership. So please join me in welcoming Sandy Faber.
That was probably the nicest introduction I ever got, Eugene, so that was just classic. Thank you so much. So maybe this is the kind of thing that you think about in the waning years of a career. Why is what you've been doing important? And I'm convinced that astronomy is important. I'm partially convinced just because everybody wants to know about it. It's such a privilege to be an astronomer. You walk into a cocktail party, people say, "What do you do?" And you say, "I'm an astronomer," and man, you are nailed to the wall for the rest of the party while everybody comes by and asks their favorite cosmic question. So people, at least a large fraction of people, really care about this, and I'm trying now to ask myself and you too, why do we care about this? And not only why do we care, but why might it really be very important? So Eugene stated my thesis, this quote, which I was rash enough to make. It's the most important thing that we could possibly understand right now. And I'm going to try to defend that. You're probably going to be a little disappointed by my success in defending that, but at least it's provocative. And I expect that it will stimulate a lot of questions, and maybe we'll have some time for discussions. And please don't be afraid to nail me to the wall and make me feel uncomfortable trying to defend this proposition. Now, here is the title I really wish I had for this talk, Coming of Age in the Milky Way. But unfortunately, another famous person thought of that before me. But the premise, as you will see as the talk develops, what happens when you come of age? You become not only self-aware, but you see yourself in a larger context, and you try to make sense of that. So my premise is that that's where our civilization, our human culture today is. That's where we are. We are on the threshold of having just become cosmically aware. And what does that mean for us? So having set the stage, I will now proceed to develop these thoughts. The first part of my talk is going to be a quick resume of the history of the universe and how it makes planets. And then the next part of the talk is going to be devoted to whether or not our planet is rare and the evidence for or against. I happen to think it is rare, but that's not proven. Then I'll talk about the prospects for our planets, cosmically speaking, and the conclusion will be that we have a great planet here. And we have the prospect of long time periods that we can now play with. We have been given the gift of cosmic time, and that is part of our problem today. What are we going to do with it? We're cosmically aware, we have this opportunity, we have a challenge. What, as a species, do we have a species enterprise, a destiny? We're the first generation to be able to even think these thoughts, I believe. And then finally, I'm going to end with some thoughts about our current trajectory and how it's really unsustainable on the timescales that are of interest to an astronomer, and what we need to do about that. So lots of pieces in this talk. I better get going, otherwise I'm never going to get through it. Okay, so the next starting point here is how the universe began. It was extremely hot at an early time, and its physics was such that it expanded faster than the speed of light. This is the famous inflationary paradigm. And just when things fall into black holes faster than the speed of light, they emit Hawking radiation. In the same way, our universe, when it expanded faster than the speed of light, generated radiation, ripples, density ripples, whatever you want to call them, fluctuations. And those fluctuations, they weren't very big, about a part in 100,000. They acted as the seeds for gravitational clustering several 100,000 years later. And so that's where galaxies come from. And I am so pleased to have been an astronomer. Even if I had never discovered anything, just to be able to say and semi-understand what I just told you. Isn't that the most amazing thing, that our Milky Way galaxy, 100,000 light years across, started out as a quantum fluctuation? I mean, if you had asked me in graduate school, Sandy, would you ever be figuring this out or watching other people figure it out? I couldn't. It would be beyond my wildest dreams. I think it's one of the most subtle, deepest things ever discovered by our species. Okay, so anyway, we've now got fluctuations, and as the universe expands, that generates a gravitational instability. A peak draws in matter around it, and a valley loses matter to the surrounding peaks. And so we develop clumpy galaxies separated by voids. And I'm particularly fond of this video of what the Milky Way might have looked like long ago. You will see that it started with sort of low-level fluctuations. They grow and they merge in a sort of a hierarchical clustering way. The blue is primordial gas, hydrogen and helium, coming out of the Big Bang. And then the makers of the simulation turned that gas into stars. And gradually we have proto-galaxies here that are turning original cosmic primeval gas into stars. And so a cycle for these galaxies, a life cycle emerges. We develop these dense cores where the star density is highest. Look, see individual groups of stars. Those are the little points that you see, the yellow points. And it's quite violent, especially at early times, when these proto-galaxies collide with one another. And every time they collide, they throw existing stars into a sort of a halo. But then more gas falls in, and they kind of regrow this rotating gaseous disk. And this process keeps repeating itself. And with time, the collisions die down because things are spreading apart in the universe, the collision rate goes down, and we wind up with more or less stable, undisturbed galaxies with a structure that looks like this: a dense core, a halo of stars, and a disk of gas, of residual gas that has more recently fallen in and hasn't yet made stars. Okay? So that's the model. And the wonderful thing is that actually the model seems to match galaxies rather well. So I'll show you a few pictures of this type of galaxy called a spiral or a disk galaxy. And you can see they all have these dense centers, and they're surrounded by disks of gas that are still forming stars. And sometimes we see them edge on, as in this picture, and we can see really they are flattened objects, just as the model predicts. And of course, we live in one of these. We know because we can take pictures with fly's eye cameras. This is a beautiful one from Victoria, British Columbia. And we see the plane of our Milky Way arcing across the sky, and this is the center of our galaxy here. So, chapter 1, we now understand where galaxies came from. Galaxies are the building blocks of the universe. Once you've made them, you can think about making stars and planets. So let's turn to that. We know a lot about that as well. Excuse me, I'm a little ahead of myself. There are a lot of galaxies. This is a picture taken with the Hubble Space Telescope, the Hubble Deep Field. There are about 10,000 galaxies in this picture. The bright ones are in the foreground. The faint ones in general are farther away. And you might be sort of depressed by this picture, right? Our galaxy is just one of many. We think on the plane of the sky, if we could photograph the whole sky, we'd see 100 billion of them. We don't seem very special at all. And so maybe astronomy is really a very depressing subject. And that reminds me of a company that I love. I'm sure you've seen it. You know the Despair Company? And they have these wonderful posters with a picture and then a saying underneath them, guaranteed to make you feel really horrible. So I made a Despair poster out of astronomy. Okay. All right, so when I get to the end of my talk, you'll see I don't really believe this at all. So I'm setting up my premise. All right, now we've made galaxies. Let's think about how galaxies make stars. Here's a nearby galaxy that's full of gas, has lots of raw material for making stars, has a region in it that is a stellar nursery. Let's blow it up and look at the picture with the Hubble Space Telescope. Beautiful detail. We see many regions like this. These are a bunch of young stars in here that have just turned on. They're extremely hot, very luminous, and their energy has ionized the birth cloud and caused it to glow. So this is the typical structure of a stellar nursery. Some of the most beautiful pictures with Hubble are of regions like this. This is called the jewel box, the young cluster illuminating the birth clouds from which it was born. Perhaps my most favorite Hubble picture is this one, though. I love this one. This is a little bit more complicated. Here's some bright stars that are sending out rain of photons, like Bryce Canyon. And here's a denser region that shields the gas underneath from the rain of photons. It's like Bryce Canyon. A rock shields the rock underneath it. You get these pinnacles. These are the Bryce Canyons of the galaxy. And in addition, very cute, here's a little star cave. Here's a young star whose photons have excavated a volume around it, and it's just sort of peeping out, and you can see it through the hole that it has made. Beautiful, absolutely beautiful. Now, in regions like this, we actually see evidence of solar system formation. Here are 4 objects from the Orion Nebula, which is one of the nearest star-forming nurseries that we have. And you can see these are protosolar disks. These are making planets. Here again, these are planets. And they're big, bright stars not far away whose photon rain is trying to blow off the gas here in a kind of stellar fratricide. So it's a race against time. Will the star form, or will it be evaporated by its big brother? Some of them make it through. These are the more developed ones. And here's a protostar and its disk of protosolar nebula. And here are 4 examples. We know that they're flattened rotating disks with the morphology of our solar system because one of them, providentially, is seen edge on, and we can see the light of its star peeping up above the disk. So you'll notice that these protosolar nebulae are dark, and that's because they're populated with dust grains. And dust grains are the seed of planet formation. They're kind of sticky. This interstellar dust is made in supernova explosions and also in the atmospheres of aging stars, blown out into interstellar space, where you can see it as dark clouds. And it's really kind of like cigarette smoke. It's about the same size as cigarette smoke particles. And when you have a lot of it along the line of sight for many light years, it's quite opaque and absorptive. When it falls into a solar nebula, the particles stick just from surface activity, and then they grow, and gradually they come to form rocky cores, and the rocky cores bring in more gas, and that's how Jupiter formed. The rocky core by itself is our Earth all alone. So here is a sort of picture of a rotating protosolar nebula. I won't try to start it. It rotates and it makes asteroids, and the asteroids get together and make rocky planets. So I love this particular picture taken by a very gifted photographer, Wally Pakolka. And he claims that this is an actual photograph, no touching up or anything like that. And it's taken in New Mexico, looking out of a cave. And I love it because there are all these terrestrial rocks in the foreground, and here's the material of the rocks right out there in the galaxy. That's how we got rocks on our planet, was putting this stuff together. So we really are truly made of stardust. There's a beautiful completed cycle in this picture. Let's now consider we've made planets. You see, I'm going along at a good clip. I made galaxies, now we've made planets. Let's consider the question of whether our Earth is a rare kind of planet or not. We now know that there are planets all over the place. The question is not planets, but Earth-like planets. So astronomers and physicists in general have made a huge amount of mileage with something called the Copernican Principle. The Copernican Principle simply means, the way we use it, that the rest of the universe is like we are. There's nothing special about us. And this has worked over and over again. Other stars are like the sun. Other galaxies are like our galaxy. Other atoms are like our atoms. The laws of physics are the same everywhere. We don't have special laws of physics here. You get the idea. And in fact, this is such a wonderful principle. We can study events here, and then we can assume if something is true here, like a law of physics, then it's true throughout the entire universe. Very powerful. Sometimes called the principle of mediocrity, which I think is kind of a bad name, but some people like it. Or the conclusion, if we now apply it to our planet Earth, would be that Earths are common. And you can do some arithmetic to show that that might be true. There's something called the Drake equation, which was invented by Frank Drake, let's see, in the 60s, I think, so some time ago now. He was curious with Shklovsky from Russia. They were curious about the number of detectable civilizations in the galaxy, and they have this equation. The number of civilizations that you will see is proportional to some number of stars, together with a bunch of factors. And there are 6 factors there. And supposing you just assume that each factor is 10%. And then you apply that to the number of stars in the galaxy, which is 100 billion, 10 to the 10th. That leaves you with a prediction of 10,000 civilizations. So that looks like a rather fecund, fertile number of civilizations to think about. And it's very inspiring. You might go off and actually try to find them. And Jill Tarter is in the audience here, who has made her lifetime performing and perfecting that technology. A contrasting view might be that the Earth is rare, and that was developed in this book here, Rare Earth, Why Complex Life is Uncommon in the Universe, and the basic reason is that Earth-like planets are rare, according to these authors. This would be the principle of singularity, or Earths are exceptional. So how does that work? They have an equation too. And they have 10 terms. So if each one of those terms is 10%, then, and we multiply by 100 billion stars, we have one Earth in the galaxy. So this is the crux of, I'm not taking a stand here. We don't actually know the answer to this. The only way to do it is to go out and observe the way Jill is doing it and others. But I'm going to entertain, just for the fun of it, the notion that maybe we are rare, and why might that be? So let me talk about a few factors that were discussed by these authors. In order to have an Earth-like planet, you have to start with a good star. So let's skip over this rapidly. It's well known. The star can't be too hot because it has ionizing radiation, and hot stars have short lifetimes. It's taken 4 billion years of sun radiation to get to the point where we are, so we can't have a star that lives only a few million years. It can't, though, be too cool, because cool stars have dangerous flares on them, and they have a habitable zone that's rather narrow. What we mean by a habitable zone? The habitable zone is only actually one of many factors that you need to be habitable, but it is defined more or less officially as the region from a star in which liquid water on the surface of the planet, water on the surface would be liquid. And so here you are too hot, here you are too cold. For this star, right about there, you have liquid water, you're in the habitable zone. So why are little stars a problem? Here's a picture of bright stars, solar stars, and these dim stars called M dwarfs. So now I'm talking about the problem with the M dwarf star. It has a very narrow habitable zone close to its star, and it's thought that planets actually become tidally locked to the star, the way our moon is locked to the Earth, with always one face facing Earth. In the same way, this planet would have one face always facing the star, and actually we found some planets like this. And it is noted that that would be a very strange planet to live on, because you always have day on one side and night on the other side, which would generate enormous winds and a very strange climate. Whether or not that's good enough to preclude intelligent life, we don't know, but it certainly is not a favorable situation based on our experience. Okay, more about the star. You need a stable solar system. You don't want to turn on the radio one day and newsflash from CNN. Astronomers have found that planet Earth is headed for outer space at a speed of around 30 kilometers a second. It's been ejected by a gravitational instability in the solar system. We've seen this coming, but we just didn't tell you about it. And at the rate we're going, we have maybe a month or two of warm weather left, and then, you know, write your will, but don't bother because nobody will read it. Yeah. Okay, so we don't want that to happen. And it's very nice that our solar system actually is a very stable thing. This was a question that was posed a long time ago by Laplace, and we didn't know anything about its stability. It's a complicated system with Jupiter and Saturn pulling on other planets and so on. It couldn't really be studied until you had a very fast and accurate computer. That has now been done, and it's been shown that our solar system is very stable for at least 1 billion years. Okay. So that's something that we can rely on, and the reason it is that it has a lot of circular orbits that are well spaced away from each other. And by the way, parenthetically, many of the solar systems that we're finding from extrasolar planets are not like this. They have eccentric orbits in them, and their orbital structure is wildly different from ours. Okay, the sun making this planet has to be metal rich because we need rocks in order to make terrestrial planets. That's heavy elements. And you should not be too close to the center of the galaxy because there's a flaring black hole there periodically, and you don't want to be too close to it when it chooses to go off. So we're safely located in the boring suburbs of the Milky Way. All right, now you've got to have a good planet. You can't be too big because you'll have the wrong composition and you won't have a solid surface. You can't be too small, though. I'll say more about that in a minute, because your atmosphere escapes. Mars is an example of that. And if you're small, you cool off too fast, and the iron core, which drives the dynamo that makes our magnetic field, you don't have any magnetic field to shield you from the onslaught of the solar wind. And that solar wind constantly blowing on you for billions of years blows away your atmosphere. And that's also happened to Mars. Okay, so let's say more about the Earth's interior, because in our solar system, at least, it is extremely special. We have something on our planet called plate tectonics. And what is this? We have a hot core here, heated by radioactive decay. So energy wants to flow out, and that creates these convection cells. The convection cells are not enough, though. You need the right kind of crust in order to have a convection cell pull down material so that it subducts. The net result is that our crust is constantly being recycled on our planet on a time scale of several 100 million years. And this cools the surface, causing the core to convect, and powers the dynamo. This is the amazing thing, not known for that long. This is actually our thermostat, this process, because if we generate too much CO2 in the atmosphere, then it actually joins with the rocks and gets subducted. At higher temperature, it's called rock weathering, goes into the rocks and gets subducted, pulled out of the atmosphere. And this, over the course of our history of our planet, has kept us thermally regulated. When we get too cold, the cycle goes in one direction. When we get too hot, it goes in the other direction. This is probably what President Trump is relying on. I haven't had a conversation with him on this, but you know, he's up to date with the latest findings. I think somebody forgot to tell him, though, that it's a cycle of several 100 million years, and it's not going to do us any good. Good over cosmic time, but not on shorter time. The last thing that this does is it builds continents. It creates land. Some people have claimed that in the beginning we had an ocean and there were just a few volcanoes like Hawaii sticking up over it, and we actually built the continents over time. That happens because as the subduction occurs, some land scrapes off here on the edge of that other continent and builds its mass. So altogether, plate tectonics is absolutely crucial for the world as we know it. Let's talk about water for a minute. Water, hard to get and even harder to keep. Important for life, but here's something you might not have realized. You've got to have water hydrated in the rocks of the crust in order to make this subduction process work. So if you don't have water hydrating these rocks at the boundaries here, you don't have plate tectonics. So that's going to have consequences in a minute. We have quite a lot of water. We don't know where it comes from. It's controversial. Did it come from comets? Was it older? Did it come from Vesta-like asteroids? We're not sure. But in general, there's probably less water close to the sun and more water farther out, because closer to the sun is hotter and the water would vaporize. An example is Venus. It lost its water. Too close to the sun, too hot. Mars also lost its water because it was too small and it didn't have this protective magnetic field. Think about a couple of coincidences here. The Earth has just the right amount of water to fill our ocean basins. Have you ever thought about that? I just thought about that about 6 months ago. I don't think anybody could predict that, and yet that is a major, major feature of our climate, because ocean circulation is a huge factor in distributing heat around the planet. By the same token, I didn't put it on the slide, have you ever thought about the size of our atmosphere? It's very thin, but it's not zero. If it were much thicker, we'd probably have a greenhouse effect of some kind. And if it were thinner, we wouldn't be able to have life on Earth. We wouldn't have an oxygen atmosphere, et cetera. So on the subject of rare earth, those are two coincidences that, as far as I know, are unexplained and yet very, very important to the history and evolution of Earth as we know it. All right, let's talk about Venus. A cautionary note. A study in tipping points, almost the same mass and radius as the Earth, but just slightly closer to the Sun. Today, it has a whopping atmosphere, 90 times Earth's pressure, mostly CO2. The CO2 came out of the rocks. Very hot there. No oceans, no continents. Why? What actually happened on Venus? Well, being closer to the Sun, it stayed hotter longer. It probably got less water in the beginning. And what water it had, it was just hot enough to vaporize the water out of the rocks. Now, something they're not teaching us in school is that water is actually a more powerful greenhouse gas than CO2 is. And so when the water went out, there was an initial phase 1 greenhouse effect on Venus, and it started to get hot. And it got even hotter, and the CO2 outgassed out of the rocks, and that was a total greenhouse runaway, and that's why Venus is the way it is today. No water makes the crust rigid. That means that there are no plate tectonics, trapped all the heat inside a planet, has massive volcanoes that are sort of stuck in place, that are just building these big shield volcanoes because they don't move around, because the plates don't move, and they repeatedly resurface the planet. Altogether, a completely different kind of planet. No water, plate tectonics, no magnetic dynamo, magnetic field, no continents, no mountain chains. All just due to being slightly closer to the Sun. All right. My last point about a rare Earth hinges around our potentially crucial moon. This is controversial, but it's something to think about. So it's generally acknowledged now that the moon formed in a giant impact about 30 million years after the Earth itself formed. And the impact had some consequences. It gave angular momentum to the planet, not only an amount, but a direction. Presumably that was kind of random. And as it happens, the axis tilt is about 23 degrees relative to the ecliptic. Not straight up and not in the ecliptic, but a moderate tilt. That gives us our seasons. And we get moderate seasons. If we were in the plane when we went around the Sun, winter, the pole would get all of its sunlight, and then on the other side of the Sun, during the summer, the other pole would get. And so it would be radically different climate. It is thought by people who model climates that a moderate tilt like this is good. Seasons may promote genetic diversity, but too strong seasons would really be very bad for higher life. Okay, so the scene was set for moderate seasons, dependable, gentle forcing function, because of a point I haven't mentioned, the moon also preserves that tilt of 23 degrees. If you took the moon away, the tilt would change, influenced by the gravity of Jupiter. So the moon has a 1-2 punch for us, the angle of our axis and preserving that over time. Finally, it also gave us a short day because it imparted rotation to the Earth. And a short day is also a good thing. It moderates the day-night temperature variations, and that facilitates photosynthesis. So altogether, the moon did a lot for us, according to this argument. And how often would another planet in another solar system suffer a giant impact from a Mars-like body to produce a moon? So you can see that the factors now are sort of piling up, and that's why some authors like to say that the Earth is rare. Okay, let's talk about planets in other solar systems. Do those solar systems look like ours? Planet discovery started by discovering these very massive Jupiters close to their star, and that's because they were easy to discover using the radial velocity technique. But as we've gone on to study solar systems, we found that, yes, there are a lot of hot Jupiters, but solar systems, planets, tend to group themselves into families. Here's a plot. This is the mass of a planet in units of Earth mass, and this is the period of a planet in days. So there appear to be 3 families that we've discovered so far. These are the original hot Jupiters, close to their star with short periods and quite massive. And we're now discovering lots of long period gas giants that look like Jupiter and Saturn. We put those planets on this graph. And then completely surprising everyone is the discovery of these so-called close-in super-Earths, which here's the Earth here with a period of 365 days. So these folks have periods of more like 10 days or so. They're really quite close to their stars. So to a great extent, the fact that we haven't found anything here may reflect the fact that those objects are hard to see. So this is where we would find Earth-like analogs. They're not very massive, they're far from their stars, hard to see using the radial velocity technique. So there are folks here who are worrying about this, trying to estimate from the tenuous discoveries here on the edge of the known region, trying to extrapolate, trying to figure out how many planets there might be in this pretty much basically unexplored region thus far. And it's thought that there could be a lot of planets there. The claim is maybe 20-25% of stars have Earth-like planets in this region. I just point out, though, that we have 3 planets in that region, and we've just seen that only one of them is any good. And so just merely, when you read in future newspaper articles about discovering planets here, just remember this argument that just merely being in this part of the diagram doesn't necessarily mean that you're going to be a good planet for life. Let me pause there for just a second. And I'm clearly not answering this question, is Earth rare or not? I tend to think it is, just because of all those arguments, including the moon and all of that. But let me return to the premise of my talk, that this is very important information for our species. So in 100 years or so, if not before, I believe we will have answered this question. And we will know what's here, and we'll know more about what they're like. So envision 2 outcomes. One outcome is that there are a lot of Earth-like planets here. How will we respond? I think we'll be energized because we have an explorer gene, and this will be encouragement to us to preserve our civilization, our planet here, so that we will have the wherewithal in future when technology develops to go out and find those other planets and see what they're like. So there's going to be a big incentive. That's what I mean by important knowledge, knowing something in astronomy and then doing something about it, planning for it here on Earth. Consider the other alternative, that further work shows that this is an arid desert and Earth is extremely rare. What's the reaction? It seems to me that we will, in this case, be motivated by our admiration and love for rarity. I think we also have this in our genome. We admire and appreciate things that are rare. We regard them as precious. And in the same way, we will have the same motivation, I believe, to go forward and protect our Earth environmentally, just as we would have had in the other case. So either message is going to be very important for the future of our species, and I think will provoke a great deal of discussion from the standpoint of, do we have now a joint mission that we should engage in to exploit the potential of our own planet or to visit other planets? Well, in order to do those things, we have to have a future. So let's consider for some short period of time the questions of the things that might threaten us, dangerous cosmic disasters. Did you know, by the way, that disaster is Latin for bad star? Disaster, okay. All right, so the first disaster that will occur and is inevitable, the sun is aging, it's brightening, and this is going to slowly heat up our atmosphere. And paradoxically, you would think that at the rate this happens that we would have more CO2 in the atmosphere? No, it's going to increase the chemical processes of weathering, and weathering puts CO2 into the rocks. And so it's estimated that 600 million years from now, there won't be enough CO2 in the atmosphere to have photosynthesis, and this will be the end of agriculture and green plants as we know it. So the conclusion from this disaster, which is unavoidable, is that we have a few 100 million years to a loss of habitability on the Earth from this cause. Another kind of cosmic disaster is that we might have a supernova explosion. Well, we know the rate at which they go off. If it's within 30 light years, we're in trouble. The frequency is such, and you can calculate that we're going to get one every few 100 million years. Again, conclusion, few 100 million years to loss of habitability. Same number. All right, cosmic impacts. We know about the famous Chicxulub asteroid, which killed the dinosaur. And people now calculate the effect of these impacts. A 10-kilometer collision destroys all higher life, and 1 kilometer wipes out agriculture by putting a great cloud into the atmosphere and blocking the surface. So the frequency is about 1 kilometer, lands about every million years, 10 kilometers every 500 million years. Now, the good thing about asteroids is we can see them coming, and we're already searching for them. We're finding all objects that are bigger than a kilometer, and diversion is possible now to 140 meters. So if part of our project is to thrive here for several 100 million years, it is inevitable that we've got to have a better diversionary strategy. So I'm assuming we can do that, and they're going to be a major inconvenience, but we'll have technology to divert up to a kilometer. And that gives us, again, something like a few 100 million years. Then we have ice ages. Ice ages are not understood. Multiple factors having to do with the Earth's orbit, small changes in the Earth's axis, et cetera, the continents move around, the ocean circulation changes. But the conclusion is that mammals have gotten through many, many ice ages. We're going to have troubles with this. We're going to have to move around on the planet to adjust our agriculture and so on, but major inconvenience, but does not affect our habitability. And then the last disaster is actually the most serious, and that is supervolcanoes. There are two kinds. There are kinds that put a lot of ejecta and ash into the atmosphere. They're not so horrible. The really bad ones are the slow ones that put huge areas of lava out onto the planet. And the biggest extinction in the history of the planet was the Permian extinction, which was thought to, that's 250 million years ago, and that was thought to be caused by one of these volcanic episodes on the Asian continent. So we get massive explosion every million years or so, but modern mammals have clearly suffered through those and survived. It's not clear whether or not we could survive one of these large igneous lava eruptions. We don't know how often they occur, could start tomorrow, but let's estimate 100 million years to loss of habitability. And that's the shortest number actually in my list. The others were all several 100 million years. But the net result is that we have a good place to exploit here for quite a large number of years going forward. And there's some lessons that we've learned here from cosmology. The first lesson is that we got here according to the laws of physics. And we're subject to those laws and must live within them. Obviously, what's hidden in my mind here is that there are no miracles. No miracles were required to get us here. You might think that this is somewhat limiting. We are subject to these laws and must live within them. But actually, it gives us a certain degree of predictability because the laws are predictable and we don't have to worry about some angry God striking us with lightning and obliterating the planet. We can predict our future precisely because we are subject to these physical laws. So I consider that a great benefit. Lesson number 2 is that the Earth will provide a livable home for at least 100 million years and maybe even longer. And so we have been given the gift of cosmic time. What will we do with it? And as I was saying earlier in the talk, I believe we're really the first generation of human beings to be confronted with this major challenge, to even think about it. Now, I'd like to talk about the thing that we're doing these days, which clearly has no future, and that is our habit of growing. You know, you read in the Wall Street Journal that if we're not growing at 3.5% per year, we're actually falling behind. I'd like to have a discussion with you of why it is so ingrained in people's thinking that a moderate growth is like standing still and not growing is like falling behind. How did we fall into that notion? I have some theories myself, but I'm just going to leave it there as a fact for the moment. So as I say, 3.5% is a target growth for our economy. And what happens if you put those factors together year after year? Then you have a doubling time of 20 years, and over a lifetime, 80 years, the factor grows by 16. I'm verging on 80 now. While I wasn't even noticing, our GDP has grown by a factor of 16. Do we really think, as we look around our planet and the limitations today, that it can grow by another factor of 16? I'm very pessimistic about that. And I note that now we're struggling around a growth in our country of about 2%. So could it be that we are actually beginning to sense the end of the glory days of exponential growth on Earth? And let me just point out, this is very important. This is what your pension depends on. I want to talk about to economists and learn more about really how the economy works. I suspect that the fact that you put money in the bank, you used to be able to do this, by the way, you can't do it now. You could put money in the bank and get 3% per year. Now we're lucky if we get 0.1%. Is that temporary, or will we return to quote unquote normal? I don't know. But I do know that people who are running endowments are pretty convinced that they can't depend on that good old 5% return per year anymore. So anything that depends on depositing money now and getting more in the future is potentially very risky. And this might be the first cataclysm to affect society as a result of hitting the limits of what the Earth can support. If I were a young person today, I'd be thinking a lot about that. All right, so supposing this miracle of compound interest goes on for cosmic time, 3.5% every year for 100 million years, what happens? Okay, so that's the number. Okay. So as a result, I don't have to turn the equation around and tell you what the growth rate can be. Effectively, zero growth if we are going to be in equilibrium with our planet for any length of time that is astronomically meaningful. So all this talk about sustainability, really, people have not confronted this. And that's one of the messages I wanted to bring to your attention in this talk, and maybe we can talk about it more in a few minutes. All right. So what is sustainable growth on cosmic time? The answer is zero growth. So what's the solution here? Here's one solution. Okay, I pulled this out of the air. I really have no justification for it. I call it the 1% solution. And what do I mean by this? It's a society that is not growing. Somehow it's replaced capitalism and our economic system with something else, maybe more like Eskimos. Eskimos don't grow economically, right? Or they didn't historically. Okay, so everything we get that's interesting today comes from having lots of people. People are interesting, they think up new stuff, they produce novelty. So in my scenario, I want as many people as possible, but, and here's why I pull it out of the air, I really think the environmental impact has to be much, much less than we have today. We have to rely on the Earth to recycle things for us, and that includes absorbing waste. So I just say that this society is going to produce 1% of the current level of waste while maintaining an adequate standard of living. Now, how many people will be in that society? Standard of living is really set by energy consumption per capita. If we assume a factor of 2 gain in efficiency over what they're doing in Europe these days, which is a factor of 2 better than here, then we come up with a world population in this scenario of only 50 million people, and that corresponds to the start of the Iron Age, which was 1000 BC. It's like 2 Californias or something like that. It's not big, not big. But you see, most of the planet is unmolested and can do its thing and maintain the biosphere, and we're not stressing it so much. Now, is this a good place to live? Well, clearly, the index of whether it's a good place to live is the number of astronomers that it has. So, astronomers live at the top of the technological pyramid, and I'm assuming that this society will have a similar technological pyramid. So if I just take per capita the same fraction, this society has 100 astronomers. Okay, I'm making a point though. I'm making the point that it's all very well to say that we need fewer people, but there's a price to that, a really severe price. And the reason why we got into this fix here was it was a sustainable society assuming the current human genome. So I know that genetic engineering is difficult. I know that it's not obvious that our descendants are going to be machines instead of people, but I do think in order to preserve novelty, we have to have a better way of using energy to create complexity. And whether or not we create little human beings who think great thoughts with smaller brains, or whether or not our descendants are quantum computers that can compute 10 to the 30th times more efficiently than IBM can today, I don't know what the avenue is, but I really think that the solution is going to be something along those directions. Okay, I'm nearing the end here. Remember this famous film. It's a wonderful film, okay? So this cartoon dates from the Bush-Gore election, and it speaks for itself. That was his film, An Inconvenient Truth. It's true as far as it goes, but this is the reality. That's what I've been saying. If we're really thinking about a long-term future on Earth, cosmic reality has puts pressures on us that we haven't even begun to dream about yet and taken into account. And as I say, we're really the first generation of people to do that. So that's kind of my ending message. Let me point out that we are now faced with a suite of new and thorny moral issues. What are our obligations to future generations? Do we have a custodial responsibility for the Earth? If the Earth is rare, maybe we should make a galactic planetary park out of it, the way we make a park out of Yosemite. Maybe the Earth will turn out to be a planet of special worth. Is there any intrinsic value in our activities? If the universe is pointless in the large, which is what Steven Weinberg has said, how do we, our intelligent beings, find meaning? Do we have a destiny? And depending on what we think about these things, I personally think that our value system is bound up in our genetic code. Some people think it comes from God. I think it comes from our genetic code. Either way, these are not easy things to change. And our value system right now is pushing us in the direction of growth. Everybody wants to start a company, and what do? They want it to get bigger. It's reflexive, it's built into us, and we have to get beyond that if we're going to have a sustainable society on cosmic time. I'll end with a couple of pictures. So this is, I think, one of the most stunning pictures ever taken by astronomers. This is a picture of Saturn, and it was taken by the Cassini spacecraft from behind Saturn, so that the sun is in eclipse. It's somewhere here behind the disk. But I'm not showing it to you because it's a picture of Saturn. I'm showing it to you because it's a picture of Earth. Here's Earth, as seen from Saturn. Okay? So this is perfect material for a despair poster. Okay? And so many people have said this, looking at this picture, that, you know, it does seem to say that, but I'd like to encourage us in another direction. There's another picture we should be thinking about. Okay, this was a picture taken by Apollo 17. This is the picture that triggered the environmental movement. For years, I saw this when I went to my car dealer. It was on the wall, and it was encouraging me to recycle my oil. And it was trying to remind me that I had a duty to do that, and I was supposed to be saving the planet. Let's focus on that. That's what astronomy is all about. That's why astronomy is important. And the message of astronomy is laying the groundwork for the future of Earth. Thank you.
Thank you, Sandy. I might mention the word catastrophe also means bad star.
Right.
As to the importance of the moon and the specialness of our planet, the rare earth argument, you know, the history of exoplanet discovery shows that using ourselves as a model is kind of dangerous.
Yes.
I know you'll agree on that.
I will agree. Mm-hmm.
You know, even Mars, after all, is a 23-degree tilt in a one-day rotation period. That doesn't mean it's fit for life. But who knows what will happen when you discover the first exoplanet living systems. They're likely to be very different from our expectations. I think that's a fair prediction. So, you know, I don't disagree with you really, but I'm just reminding us of the wide variety of possibilities beyond what we may imagine now.
I agree with what you're saying. I would say, though, that I'm not claiming that an axis obliquity of 23 degrees means you have a good planet. You have to have a lot of other things, you know, all those other 9 factors. But I think you did bring up a very good historical point. I remember when I was a graduate school at Harvard, and I heard an astronomer, I won't name his name, but he was making models of the solar system, and they were perfect models. They made little rocky planets in the middle, and then they made gas giants at the ice line, and then they made smaller planets. And it was all presented that this is the way we make a solar system. We had one example, and he made that. So I guess I would take your argument and turn it around on myself and say, I would apply it to life. Is this the only way that we can make intelligent life? And it's very hard to do science with one example. And these are both in that category.
Can we to consider living on moons and planets orbiting on some of the gas giants?
Can we consider
Living on a planet orbiting around the gas giants, Jupiter?
I don't think we can consider living on them as the beings that we are now, but it's a perfectly good question to ask whether there are other beings on those planets. In particular, Europa has a subsurface ocean with probable hydrodynamic vents, and maybe that's where life started on Earth. Maybe there are organisms under the surface in Europa.
Yeah, in the back.
I'm actually studying architecture, so I'm coming from a completely different place. But I did have kind of a question to some of the cultural implications that you're kind of talking about. So, like you were mentioning this photo of the whole Earth and how it kind of spurred a conversation about the environment in a way that never happened before. And in architecture, I feel like in like past epochs, a sort of sense of cosmic design coded into the buildings themselves. Something that helped people understand not just their place in whatever civilization it was, like how big the span of time was like on a more cosmic scale. But you were also saying that you feel like the changing these kinds of things is something that must happen on a genetic level, or on a, also positive like on a religious level. Do you think that there are ways to code cosmic time into our everyday experience so that way we start to think about things in this kind of long-term way?
I think we need to think about this. A very good question is, where in our genomes does our personality reside? Rather than coding in cosmic time, what I think we need to do is we need to code in a sense of value and enjoyment that is not associated with growth or the acquisition of more stuff or controlling larger and larger forces. So it seems, and you see that is so antithetical to all the evolutionary pressures of the past that it's a profound genetic change. And I don't know if we can do that or not.
Yeah.
I'm wondering what you think about, you mentioned that the solution is no growth, but isn't it possible, or do you think it is possible for mankind to make it into space in a meaningful way?
I think it might be possible eventually, but I bet everybody would agree that we're going through some sort of nexus in the next 100 to 200 years. And I don't believe that we'll be meaningfully in space on a time scale to help the population problem or the resource problem on that time scale.
There was a question to my right, yeah, right there.
Do you think it's a genetic recoding or just a cultural rethinking? Like, do you think it's an Americanistic capitalistic sort of mindset that you're saying that needs to be encoded, or more of like a human problem, like something that goes over all cultures all over the earth?
Excellent question. I mentioned the Eskimos as people who didn't seem to be so concerned with, and I picked them at random. I really don't know anything about Eskimos. I was just trying, if there are Eskimos here who are insulted, I apologize. I was just thinking that more, less advanced cultures where life moved more slowly, maybe this tendency was not as pronounced as we see it today. Maybe it's brought out because the possibilities of growing a lot within a single human lifetime are bigger for the average person than they are now. So I think you've raised a really great question. What is our human nature and how malleable is it? And I don't know. It's one of the many questions I've raised here. Mm-hmm.
The 100 million year time scale is pretty comforting, but coming from the environmental science discipline, we're going to kill our own species in like 300 years if we don't get our act together. So
Right.
How do you go about making people care about an astronomical time scale or like a planetary time scale when day-to-day life is just not about that right now?
Right. So I'd say two things about this. First of all, I think you've made a wonderful point. How are these points even relevant? And surely they are not very relevant to people who are just looking for their next meal. You know, this is to think thoughts like this and actually maybe take some action in that direction is a luxury of people who have already met their basic needs. So that's a wonderful question, and I just don't know what to say about it. But we have all kinds of decisions facing our planet, and if the attitude always is, well, most people will never have the luxury to think about it, we won't be able to make very much progress.
I guess my question was, how do you go about trying to make people care about this cosmic time scale? I'm trying to help people care.
So I gave you two arguments. They were both astronomical, and they both revolve around whether or not we find that there are other planets. And if we find that there are other planets, I think we have great motivation as a species to go to exploit that. By the same token, if we find out that there's only one, I think we have great motivation to solve our problems on this planet. So I think either way, we need some way of inducing people today to think that there is a future that they would sacrifice for. And so telling people that this is a wonderful planet and our species could have a collective goal and destiny is a way of sweetening that argument. How do we get people to do less in their own lives in order to save more for future lives?
There was one in the back, maybe? No? Okay, we'll take the one in the middle.
You mentioned that it's quite crazy that here on Earth we have the perfect amount of water to fill our phases, just rightly so. Why is that so crazy? Was Earth first very rocky, these concave places where ice just came and filled them perfectly, or was it a mix of the two?
No, it's a question of how the water got onto the planet.
Right.
And so there are two schools of thought. One is that it came in, mixed in with the rocks of the asteroidal-like protoplanetesimals that coalesced. Another school of thought is that it came later from comet bombardment. And the moon impact is important here because the moon heats the Earth to a very high temperature. And it has been argued by some that a lot of the water, had it existed, would have gotten driven off in that time, in which case we needed a secondary source, and that secondary source just happened to have the right amount. So it's an amount question, which you try to argue with many imponderables in histories that have different avenues.
Take two more. Which one I saw first?
Relating to the question the lady in the back mentioned about 300 years from now, and the problems we're going to confront 300 years, do you ever think that maybe it's part of our destiny to be gone in 300?
Many people say so. Say that, right? Mm-hmm. I find that very sad, right? And the question is, do we collectively feel sad enough to do something about it?
One last question, right in one of them.
This sort of relates to the 300-year question in a sense. It's hard to imagine an equilibrium that lasts for 100 million years. So I wonder if there's a dynamical solution. Think about your comment about the mammals surviving multiple ice ages. Maybe our future is a series of catastrophes,
Yeah.
which basically thin out the population, and then there's a period of recovery again.
Right. Sometimes I think that maybe pandemics are not such a bad idea.
I was going to say that might be another poster of despair.
Yeah, right. But really, if you look at the history of pandemics, there's never been anything that big.
Okay, great. Well, I think our time is up, so let's thank Sandy.
Okay. Thank you.